what I'm going to talk about today is based on these two works with collaborators Tim Cohen, Nathaniel Craig, and Xiaoshuan Liu. And the underlying theme is how we use geometry to map from EFT Lagrangians to amplitudes. So underlying all of this, as is often the case in EFTs, is the field redefinition redundancy of an EFT Lagrangian. So this is that if you are a particle physicist and you're only interested in scattering processes, you can do the following substitution in your Lagrangian. Let's say it's built out of some field phi of x, and you can substitute that for some new field eta of x. This linear bit is important. And then add just arbitrary powers of eta and derivatives acting on eta, and your S matrix will not change. So on the face of it, this is actually kind of miraculous, right? So if you had a simple phi to the fourth theory and you made this substitution, well, you would get an operator which looks like it's got 4,000 fields and 16 derivatives coming out of this, this last term you can see here. And moreover, you could make the coefficient of this operator arbitrarily big. You know, it would defy any sort of natural power counting scheme on fields and derivatives that you might construct. However, that operator is going to combine with all of the other operators that this term will generate in order to just reproduce the S matrix of phi to the fourth theory. And so that implies that there is some, a lot of structure in how EFT Lagrangians map onto amplitudes. And at the end of the day, this is a lot of the reason why EFTs can be difficult, this field redefinition redundancy. It makes it difficult to enumerate a non-redundant operator basis, which is going to span all observable effects and amplitudes. And it just makes it difficult to calculate scattering amplitudes themselves and anything that you might derive from it. And in this sense, it's very similar to gauge theory, perhaps morally different, but the practical consequences are quite similar. So a 4-point amplitude in Yang-Mills, you will get contributions from these two graphs shown at the bottom of the slide. And you'll get contributions to similar structures from both graphs, only the sum of which is gauge invariant once you go on shell. And this is exactly the same in EFTs. So in a general EFT, you will get some contact interaction from the 4-point vertex on the left, but also from the S channel graph on the right. There are going to be insertions of EFT operators in the two vertices, which are going to cancel the pole in the propagator and also give you a contact term from that graph. And as we will talk about extensively, it's only the sum of these two graphs once you go on shell, which is field redefinition invariant. And so just like gauge theories, this is a good reason to just start studying EFTs on shell. And if you do that, you open up your eyes to a whole set of rich theoretical structures which might have been hidden from you in the Lagrangian. And not only this, but like gauge theories in the 90s, it starts to open up rapid practical computational routes with many phenomenological applications. And as evidence for this, just see the back catalogue in this lecture series. I've already had too many talks to list on what you can study in EFTs on shell. So what I'm coming at today is a related question. So which is what parts of an EFT Lagrangian map into amplitudes? And this is relevant for various reasons, but it can also be relevant for how do we parameterize deviations from the standard model that we might see, for instance, at the LHC. And in this sense, the work I'm talking about today is a follow-up to some work which my collaborator Xiaoshuan Liu has already talked about in this series on the differences between SMEFT and HEFT and when you need to use each to describe the low energy effects of heavy physics. So this talk is going to divide into two parts. And it's about how we can use geometry to isolate bits in the EFT Lagrangian, which transform covariantly or invariantly under field redefinitions, and therefore must map into amplitudes. And part one is going to be studying field redefinitions without derivatives. And so that means we can just work at fixed derivative order in the Lagrangian. And then part 2 is going to try to start to generalize this and look at field group definitions which include derivatives and allow us to study at any order in the Lagrangian. And at various points, I'll try and ground this discussion in what it tells us about phenomenology in the Higgs sector of the Standard Model. Okay, so this is part 1. What is our geometric picture when we're restricting to field group definitions without derivatives? Well, we can look at the set of configurations that our fields can take on at any given space-time point. So we can just look in target space. And our fields, let's just assume they're scalar for simplicity, although we can relax this assumption. Our fields are just coordinates on target space. And field redefinitions without derivatives are just coordinate redefinitions. We replace, we write phi as some arbitrary function of eta, as long as it's invertible, as long as it has this linear piece, that's okay. So ultimately, we know the physics in amplitudes has to be invariant under coordinate redefinitions. Now, our Lagrangian, at least truncating up to 2 derivatives, can be encoded as a metric and a potential. So all the 0 derivative terms in your Lagrangian can just be encoded as a scalar function v on your target space, here in orange. And all your 2 derivative terms can be encoded as a metric tensor, which indeed transforms as a tensor should do under field redefinitions. You can see grayed out here. So this gives you a hint already about how you might want to, how you can sort of understand the dynamics that's encoded in your Lagrangian in a coordinate invariant way. But ultimately, when it comes to doing calculations, you sort of want to undo this packaging. You want to settle on a vacuum, let's say without loss of generality, all phi's are 0. And you start to Taylor expand your metric and potential about this point to get a series of local operators, which you can see on the bottom line here. And so your Wilson coefficients in this general scalar EFT are just partial derivatives of the potential and metric. Now, those partial derivatives of the potential and metric are not coordinate invariant by themselves. And you can already start to think, well, how can I arrange all these partial derivatives into quantities which are covariant under coordinate redefinitions? And if you look at it for a little bit, you can start to convince yourself that these partial derivatives of the metric can start assembling into connections and derivatives of the connection. And from that, you can start assembling the potential into covariant derivatives of the potential. And you can start assembling all these derivatives of the metric into covariant derivatives of the Riemann curvature tensor. And it turns out this is all that amplitudes are in a scalar EFT up to 2 derivatives. And we'll talk a lot about how we understand this map from Lagrangians, from partial derivatives of the metric and potential into covariant derivatives of the potential and the Riemann curvature tensor. Okay, so let's just review this geometric picture in a phenomenologically relevant example, which is the description of the scalar sector of the Standard Model and any effects that might be there due to heavy new physics. And for this, I'm drawing a lot from this paper by Alonso, Jenkins, and Manohar, which has inspired a lot of the work that I'm talking about today. So there are 4 scalar degrees of freedom in the Standard Model, so the Higgs and the longitudinal components of the W and Z. And here I'm just plotting schematically target space for 2 of those degrees of freedom, just for simplicity. And there are 2 main sets of coordinates that you might have on this target space. So one is heft, and there your coordinates are h, little h, a single h, and your Goldstones, pi1, pi2, pi3. And your heft Lagrangian is just a Taylor expansion of these things, like potential and a metric, about our vacuum, this green dot. SMEFT, on the other hand, is an expansion about a presumed electroweak preserving vacuum in components of the Higgs doublet, phi1, phi2, dot, dot, dot. So you find a something like the red point here, which doesn't transform under electroweak symmetry. And around this red point in target space, you can find Cartesian-like coordinates which rotate linearly into each other in order to expand your Lagrangian. And that is what SMEFT is. I should also just add, before I move on, that our dynamics are, again, encoded as a metric and a potential on this target space. And we want to now see how that maps into amplitudes. And we'll find that the things that amplitudes probe are things such as curvatures of the manifold where we live at our vacuum, and also how rapidly those things are varying. For instance, as we move towards this electroweak preserving vacuum. Now, to motivate this, I just wanted to start off with an amplitude which is very familiar to a lot of people, which is longitudinal W boson scattering. Now, this is famously the amplitude which, if you don't have a standard model like Higgs, is going to grow with energy and violate unitarity at the TeV scale. Now, we can start to see how this works geometrically. Here at the top, I just have a generic Heft Lagrangian written in terms of some H-dependent form factors, F and V. And this N is just a nice repackaging of your Goldstone fields pi, which transforms linearly, which allows us to write down a neat Lagrangian. To get out the terms we want, we can just Taylor expand this black thing to get an orange contact term between pions and a blue interaction between Higgs and pi. And these contribute to the correspondingly colored graphs shown below. Now, the contact graph gives you a contact term shown in orange, S plus T over V squared. And the S and T channel graphs are going to give you the blue term here. And the important point is that this blue term is hiding a contact piece. And you can see this just by expanding these proper fractions in S and T, just expanding the numerator in powers of S minus MH squared. That's going to pull out a constant term, which is shown on the line below. So the thing which grows with energy, the thing proportional to S plus T, is now F prime squared minus 1 over V squared. And this is the thing which causes unitarity violation when you don't have a standard model like Higgs. Unless F prime, unless the coupling of Higgs to 2 Goldstones is exactly 1 over V, as it is in the standard model, then this amplitude is going to grow and violate unitarity. Now, as promised, all of these prefactors multiplying distinct kinematic structures in amplitudes have to be sort of geometric, covariant quantities. And here you can just see that by inspection. You can read off the metric on the previous slide and start to calculate connections and Riemann curvature tensors. And indeed, it works out like so. In particular, the coefficient which is growing with energy is just a component of the Riemann curvature tensor. In particular, this component of the Riemann curvature tensor is just a sectional curvature. So what this is measuring is in the pi plus and pi minus directions, if you restrict to just that 2D submanifold, what is the Gaussian curvature at our vacuum where we live? And that's what this sectional curvature is measuring. And if it's non-zero, ultimately, this amplitude is going to blow up and violate unitarity. Now, how do you go about calculating amplitudes more generally? Well, as we've already said, you can take your general scalar EFT Lagrangian up to 2 derivatives and Taylor expand it to get local operators. And from there, you can already read off the Feynman rules. So the propagator looks pretty innocuous. Again, it helps to work in a basis at our vacuum where the metric is diagonal. We can always do that. And the Feynman rules for the vertices look like so: a partial derivative of the potential and some partial derivatives of the metric multiplied by pi dot pj. And just by using a simple kinematic identity, writing this pi.pj in terms of some Mandelstam invariant below, Sij, and some things on the bottom line, which are proportional to pi squared, you can see exactly the problem with calculating amplitudes in a scalar EFT in a general basis. Because this very last term at the bottom right is proportional to the p squared minus m squared of a particular leg of your vertex. And if that leg happens to be internal in one of your Feynman graphs, well, that p squared plus m squared in the numerator is going to cancel the p squared minus m squared in your propagator. And it's going to remove poles. So in a Feynman graph with n propagators, you're going to get a part which has fewer than n factorization channels. Now, the way to get around this in geometry is to go to a special basis where this coefficient of this p squared minus m squared term vanishes always. And that has a nice geometric interpretation, which is an inertial frame. So we go to an inertial frame, aka normal coordinates. And this is essentially a special basis which makes the Lagrangian amplitude map transparent. Now, the properties of an inertial frame are that geodesics are straight lines. So it's a special set of coordinates which essentially trivializes the geodesic equations. So in normal coordinates, if you're going in a particular direction in your target space, in your field space, that's equivalent to moving along a geodesic as defined by the metric in your Lagrangian. And this makes partial derivatives and covariant derivatives equivalent. So if you're moving in a given direction, a partial derivative is just probing how much a certain quantity is varying in that given direction in target space. That corresponds to how much that quantity is varying on a geodesic, which is essentially the definition of a covariant derivative of something. So you can see already in red that the partial derivative in normal coordinates has transformed to a covariant derivative, a very subtle semicolon of the potential. The metric factor is a little bit more involved because you've got these non-derivative indices, these two extra indices on the metric. But you can just look in any GR textbook and it will tell you in normal coordinates, this partial derivative of the metric is a covariant derivative of the Riemann curvature tensor. And that's how you show generally how the Lagrangian maps amplitudes in this particular case. Note, of course, that the troublesome coefficient of p squared minus m squared has just disappeared. So here, these partial derivatives of the metric are proportional to covariant things, but just by symmetry, they vanish. And one fact you may know from GR is in an inertial frame, the first derivative of the metric is identically 0. And the vanishing of these troublesome coefficients is exactly the high order generalization of that. So this is essentially the answer. How do we map from Lagrangians to amplitudes here? And working in this normal coordinate basis allows us to make very efficient and very effective calculations of higher point amplitudes, which is useful for phenomenology. So this is what we did. So here we're calculating a higher point amplitude of 2 Goldstones to any number of Higgses. And we're just looking at the contact term. And you can essentially just read off from the rules on the previous slide. The contact term is going to look like this. So if it were 2 pi's going to 2 Higgses, we would have a piece which grows with energy, which is just proportional to an undifferentiated component of the Riemann curvature tensor, as before. And this is going to be equal to a new sectional curvature. So the sectional curvature in the h and pi direction, which we call curly kh on this slide. Now that we're adding more legs, we're essentially just taking more covariant derivatives of this quantity with respect to little h. And it turns out that that is just taking simple derivatives with respect to a canonical Higgs coordinate of your sectional curvature. So it's just telling you how much is the sectional curvature varying as you move in the h direction. So this is the main result from this slide. In 2 pi to any number of Higgses, the contact term of that amplitude is just going to be proportional to the derivative of a sectional curvature. And this allows us to sort of probe in amplitudes how this quantity is changing in target space. So in particular, for each of these amplitudes, we can now infer a new unitarity bound. And it's going to probe different scales in the theory. So in this arbitrary 2 to n amplitude, we can project into an S-wave component just by taking a properly normalized average over, well, integral over incoming and outgoing momenta. We'll project into an S-wave component, and partial wave unitarity says this S-wave component can't be much bigger than 1. And we use that to set a unitarity bound here. And this quantity is in vertical brackets on the left-hand side at the top. Is going to probe 2 different scales, depending on whether n is 2 or n is a few. So if n is 2, it reduces, as we've already said, to a unitarity bound, which depends on how flat things are at our vacuum, just the size of this sectional curvature where we live. However, if you start to increase n, this thing on the left-hand side, which is essentially looks a bit like a geometric mean, starts to become weighted more and more to the scale of h derivatives. So it starts to become weighted more and more to the scale of how rapidly is this sectional curvature varying in the Higgs direction. Now, ultimately, if you take n equal to infinity, this thing formally reduces to the radius of curvature, sorry, the radius of convergence of your sectional curvature. Now, we can't take n equal to infinity, like we don't have perturbative control over an amplitude with an infinite number of legs, but we can take n equal to a few. And what we'll show in some simple perturbatively matched UV models where we know exactly the form of KH, that taking n equals to a few means that this quantity becomes very, very close to the radius of convergence of this KH. And this allows us to understand some phenomenological effects in the scalar sector of the standard model. Another thing that we will see is that in many weakly coupled UV theories, there's a natural hierarchy between the 2 scales being probed here. So it is very possible to have a target space which is very flat where we live compared to the distance you have to move until the curvature blows up, which is the radius of convergence. This is what was shown at the bottom here. Okay, so let's see all of that realized in a concrete model, which is the simplest extension of the scalar sector you could possibly envisage in the standard model. So this UV Lagrangian is just the Lagrangian for the Higgs, plus that of a real scalar singlet S, and it has some mass m squared, and it has a cross-quartic kappa with the Higgs, through which it can also get some mass when you turn some Higgs background on. And we can integrate out this at loop level, and generally we're going to get functions correcting the Higgs Lagrangian, which are going to be functions of this Higgs-dependent mass, this m squared plus kappa mod h squared of S. So we can do that, and you can see the paper for details. We can calculate a metric and potential in the EFT, and we can use that to calculate this sectional curvature in the h pi directions, which is shown here. Now, the particular 2 to 2 amplitude, 2 pi to 2 Higgses that we studied on the previous slide, that can probe the scale of this KH at the origin. So when we turn little h, we set little h to 0. The 2 to n amplitude, where n is a few, is going to probe the scale, which is the distance in the complex plane of h to where this sectional curvature has a pole. So where this denominator of the sectional curvature is going to blow up. It's going to go to 0, sorry. So visualizing that on the diagram on the right, we live at the Heft vacuum, where h is 0. The 2 to 2 amplitudes measure the size of the sectional curvature here. The 2 to n amplitudes measure this distance v star to the nearest pole in KH. And the pole in KH sits directly above the SMEFT vacuum in the complex plane of H with a height which goes as this ratio m squared over kappa. Now, just imagine for a second that m is small. So this singlet S is getting most of its mass through the cross-quartic of the Higgs from electroweak symmetry breaking, at least from our perspective at our vacuum. Well, this pole in KH is going to descend very close to the SMEFT vacuum. And this means two things. So one, V star is going to be very, very close to V. So in our theory, we're going to be able to find a unitarity cutoff, which is TeV scale. And two, the radius of convergence of this sectional curvature about the SMEFT vacuum is very, very small. So let's say you matched your theory onto SMEFT and you calculated a metric order by order in powers of mod h squared. And through that, you calculated your sectional curvature order by order in mod h squared expanded about the SMEFT vacuum. And you may not know that you're doing that, but you are tacitly doing that every time you calculate an amplitude, such as this 2 pi to n Higgs amplitude. Well, your prediction for that component of the amplitude is not going to converge at our heft vacuum because of the proximity of this pole. And so in this particular class of theories, the SMEFT description is going to give you bogus results. So through the position of this pole and just seeing how kappa h varies in field space, we sort of understood that there is a class of theories where things can look relatively flat, aka relatively standard model-like, where we live at the heft vacuum, but things can be varying rapidly at the SMEFT vacuum due to the proximity of a pole. And this means that the SMEFT description of these theories is not going to be very good. Now, a final slide to wrap this up. I just want to show numerically what some of these unitarity bounds are. So we look at the amplitudes 2 pi to n Higgses and vary n. And for each of these amplitudes, we calculate numerically what the unitarity bound is going to be. And we do it for 4 specific instances, A through D, of this UV model. So 4 specific sets of UV parameters. Now, on the right, we plot the unitarity cutoff that we get in units of 4 pi V star as a function of n, the number of Higgses. And you can see what I asserted previously is coming true. So for n, single digit n of 8 or 9, for n of a few, all of the unitarity cutoffs that we get from these high point amplitudes are tending to 4 pi V star. Moreover, what we can see is that there's a set of models, so that's B, C, and D, for which V star squared bar KH is small, you can see in the table. And what this means is that the unitarity cutoff that we get from looking at the low point amplitude for n equals 2 is much less stringent than, let's say, the true unitarity cutoff of the theory. And this set of models has overlap with a set of models A, B, and C, which have a V star which is close to V. So these are things with a TeV scale unitarity cutoff, which are non-decoupling and which are poorly described by SMEFT. And again, this means that there are models B and C where things appear very, very standard model-like in low point amplitudes where we live, but things around the electroweak preserving vacuum are really messed up due to the proximity of a pole. Now, in this paper referred to in gray at the bottom, we took models like this, but also gave the new fields electroweak charges, and we considered their contribution to certain observables like Higgs to gamma gamma, which is often a good observable for non-decoupling physics. And we found that many of these extensions of the standard model scalar sector are still viable. interestingly, these models, because they mess up the electric preserving vacuum so much, they're good candidates to provide a strongly first order electric phase transition. And so my collaborator Ian Banter in this second paper at the bottom has investigated the parameter space where that is viable, and it overlaps quite nicely. So through this geometry, we've managed to identify a very interesting phenomenological class of models. So that's about it for part one. So that's field redefinitions without derivatives. And maybe at the end of this slide, if you want to ask, if you had any pressing questions, that would be a good point to ask. The main takeaway is that measurable quantities are geometric. And so we saw just in a general scalar EFT, which we truncate up to 2 derivatives, your Wilson coefficients are just partial derivatives of a metric and potential, but they have to assemble into covariant derivatives of the Riemann curvature tensor and potential in amplitudes. And it's through these quantities that we can probe things like sectional curvatures and other curvature invariants and how they're varying in target space. And through this, you can actually do some interesting phenomenology. So in particular, we calculated some 2 to n amplitudes, which effectively measure the distance to a pole in a curvature invariant. And we use this to understand a class of models which are poorly described by Smith. And that's it for part one. And what I'm going to do in part two is talk about what happens when we go beyond 2 derivatives. But I'll just leave a slight pause if there are any pressing questions. Okay, so why go beyond 2 derivatives? Well, this is tied up with the question of how do we deal with field redefinitions with derivatives? So let's say, again, we have our general scalar EFT up to 2 derivatives built out of the phi tildes at the top. Well, we are completely free to make the field redefinition shown on the following line, which is phi tilde equals phi, plus this 2 derivative term times this completely general tensor H. And what that's going to do is it's going to shift the metric as shown in the following line. And what this means that apart from special points where the potential is extremized, we can change the metric to be whatever we want in field space. And so we can change how the metric is varying in field space. We can change how things derived from that, like the curvature is varying in field space. And so the notion that this is invariant, which I've been relying on in part one, is completely invalidated. Of course, amplitudes are still invariant under this, but the physics we need to patch everything up has been pushed to higher derivative order, 4th derivative order, and so on and so forth. And so this is why we really need to understand field redefinitions with derivatives in tandem with high derivative structures in the Lagrangian, because field redefinitions with derivatives are just going to scatter the physics that we need across different orders and derivatives in the Lagrangian. And if you're being kind, you might say, well, okay, that's a theoretical possibility, but you've just shown us a case where you can derive some interesting physics from a Lagrangian just truncated to 2 derivatives. And maybe you're just doing a boneheaded field redefinition, just vandalizing the theory, but actually it's okay. Unfortunately, that's not quite true, because we're all inadvertently doing field redefinitions with derivatives in EFTs all of the time. And this is because how matching behaves. So let's just say you had a simple UV model, like a 2 Higgs doublet model, and you did something innocuous, like rotated the 2 Higgs doublets amongst each other to get to the Higgs basis. So the VEV at the global minimum goes entirely in one Higgs doublet and not the other. So that is an innocuous field redefinition without derivatives going between LUV and L prime UV. Unfortunately, if you match these 2 theories, the 2 EFTs are going to look nothing like each other. And that is because they are now going to be related by a field redefinition with derivatives. And so we're actually doing field redefinition with derivatives all the time. And for this and other reasons, it's actually quite important to understand how to generalize this picture to field redefinitions with derivatives. So how do we do that? Well, up until now, we've just been working target space. So we've been looking at one space-time point and looking at all the configurations of the fields at that one space-time point. Field redefinitions derivatives are going to be mixing fields at nearby space-time points. So let's just take a step back and look at the entirety of configuration space. So all of the field configurations at all of the space-time points. And let's try and understand covariance in this space under field redefinitions. Now, again, to do that, we take a step back and we go off shell. So we study correlators before all of this field redefinition redundancy is modded out in the amplitudes, which are ultimately invariant. Now, step 0, let's say, to making everything look covariant in this space is to just promote everything to an index. So this is using DeWitt's condensed notation here. So we've previously been studying some phi fields with some flavor indices alpha and a distinct space-time coordinate x. And let's just promote all of these labels. So be it flavor indices, Lorentz indices for bosonic spinning fields, space-time coordinates. Let's just write that all as a single index x. Now this condensed notation has one implication, which is namely when you see a repeated index x, so sort of phi x, jx, that implies a sum over discrete indices, the alpha indices, but also an integral over space-time coordinates. And this is step 0 to making things look covariant in configuration spaces. Now, the objects whose covariance under general field redefinitions we want to study are amputated correlators. So I'll just remind you very, very briefly of the usual path integral setup, this functional methods for computing these amputated correlators. So there's a slight notation change at the top. Our fields are actually these coordinates eta, these dummy variables in the path integral. And if you add a source term, jx eta x, you can build the functional w of j. And w of j gives you all the connected correlators. You can go further than that and do a Legendre transform to get the effective action gamma of phi, where phi is the classical field. And it's with respect to transformations of the classical field that we're going to be looking for covariance here. So phi is now the classical field. For notational convenience, we're just going to define also an inverse propagator, e to the I d to the minus 1. Sorry, minus I d to the minus 1, which is just the 2-point function of the effective action. And this is going to behave slightly like a metric. Okay, so the quantity that we're studying is the amputated correlator, which is just the nth derivative of w. But on each leg, you add an inverse propagator to remove the pole on that leg. So this amputated propagator is just going to be the sum of all ways of attaching these amputated legs into tree graphs built out of vertices of the effective action gamma and propagators id. So we're avoiding going all the way on shell to amplitudes in order to see this covariance more explicitly. But in order to get to amplitudes, the remaining steps that you have to take in Alice-Stead reduction are you set j equal to 0. And we're assuming we're at the vacuum phi equal to 0. So this corresponds to setting phi equal to 0 at the same time. And then you contract with one particle wave functions. So e to the I px, where p is on the mass shell for each particle, and any other like polarization tensors if these are if these are vectors or what have you. If you do that, you will get the amplitude out up to some wave function renormalization factor z. So you can already start to see how the quantities on the previous slide might start to generalize some of the quantities that we've already seen in target space in part 1. So in particular, this inverse propagator with 2 lower indices functions roughly as a metric. And one way of seeing why it might do that is you can go on shell, you can set j equal to 0 and Fourier transform it, and you will indeed see that the target space metric is a component of that. Now, the connection that we want to have on configuration space is this new G quantity, which is just a 3-point vertex with one propagator contracted into it. And again, if you go on shell and Fourier transform, you can find the metric space connection hidden in among it, along with different things with different derivative structures. Now, our Riemann curvature tensors and analogues of that from part 1 are just going to be our amputated correlators. So if you look at the expansion of the amputated 4-point correlator here, you can see it's already a little bit Riemann curvature tensor-like, in that the contact interaction just looks like 2 derivatives of the metric, and the naively factorizable graphs look like a product of 2 first derivatives of the metric contracted together. And indeed, we already know if you go on shell and go to amplitudes, this contains the actual Riemann curvature tensor in target space. Okay, so now the important thing is to establish how do these things construct and transform into each other? Do they do that in a geometric covariant way? So the main result of this second paper that I'm talking about is the following relation, namely that the n+1 point correlator just looks like a covariant derivative of the n-point amputated correlator. So this covariant derivative has a piece which looks like a partial derivative piece. You're just differentiating functionally with respect to the classical field. And it also has a connection-like piece where you're acting on each of the n indices in turn with this new generalized Christoffel symbol. And you can show this just algebraically. You can prove this by induction. But a way to understand what this covariant derivative relation is telling you is just that the covariant derivative is considering always to add this new leg x into your existing n-point correlator to make all of the graphs of the n+1 point correlator. In particular, this partial derivative is going to add your new leg x in all ways onto the vertices and propagators that are already buried in n. And this connection piece is going to add your new leg in all ways by splitting in an existing leg. So this is the information in the diagram on this slide. So this partial piece, this functional derivative with respect to phi, if it hits a vertex of the effective action, which is buried in your n-point m, well, a vertex of the effective action is already just a bunch of functional derivatives with respect to phi, and so it just adds one more. It just adds this amputated leg onto that vertex. If it hits a propagator, however, this functional derivative is essentially going to cleave it in two and put a new 3-point vertex in the middle with this new leg hanging off. And this is almost all the ways that you can add this new leg to the graphs. The remaining ways are given by this connection term, which is where you excise an existing leg, xi, you shove a propagator back onto it, and then you take a new 3-point vertex with the existing leg, xi, and this new leg, x. And through that, the covariant derivative adds this new leg in all possible ways into the existing graph. And that is a graphical way of understanding what this relation is telling you. Now, you might look at this and say, well, this looks a bit like off-shell recursion. You've got this identity for recursively constructing higher and higher point correlators. And that's indeed correct. And so I just want to take a minute to understand the connection to traditional off-shell recursion. So traditional off-shell recursion constructs the Taylor expansion of your classical field phi with respect to j, about the point j equals 0. The reason for doing this is because this Taylor expansion contains all information about amplitudes, because an n+1 derivative of your generating functional wj, you can always take one of those derivatives and just write that as your classical field So this Taylor expansion is going to contain, all the information about on-shell correlators. So Behrens-Gieler offshell recursion makes this Taylor expansion by iteratively solving the equation of motion for your classical field. Now, what we can do is construct those coefficients in a slightly different way. So we can write this Taylor expansion as the formula at the bottom. We have a hatted J, which is just a raised J. So a J contracted with a propagator. And then the coefficients are just these G quantities here, which behave as generalized Christoffel symbols from differential geometry. So these generalized G symbols are amputated correlators with one index raised, so one propagator shoved back on. And these guys are also constructible by covariant differentiation. So you can see the covariant derivative acting on the G at the bottom here. You're just taking covariant derivative with respect to the lower indices only, as you do for generalized Christoffel symbols. So we can construct the coefficients of this Taylor expansion that is constructed by traditional offshell recursion by this new covariant derivative relation. And we can also construct it when J is not equal to 0. We can understand the relation between phi and J at different points offshell. And hence the title of this slide, offshell recursion, but more covariant and more offshell. Now, my final slide is a very important point. So we've seen how we can recursively construct correlators, amplitudes, by covariant differentiation. But we haven't shown that the end result is indeed covariant, that it actually transforms as a tensor. So this is what this final slide is about. And here we make a little conceit. We just go to tree level. And the reason for doing this is the effective action is just the normal action. And so that we know it transforms as a scalar under all field redefinitions. So under any field redefinition, including something with derivatives, that is phi goes to phi tilde, the action is going to transform as a scalar. So if you impose that and study how m tilde transforms, so this is your amputated correlator calculated with phi tilde, you can see it is indeed covariantly related to the m without a tilde. So the m calculated just using phi. And this is the required tensorial transformation to show that we found something that is covariant under all field redefinitions. Now, this is covariant up to these terms proportional to A and B, which vanish on shell. You can see very briefly why they would vanish on shell. This first term proportional to A, well, out of all these A terms, and the full expression is quite complicated, you can pull out a factor of d gamma d phi. And this is just J, and when you set J equal to 0 to go to your amplitudes, that's going to vanish. Out of this second factor, proportional to B, you can see that the term in the dashed orange box is going to vanish because field redefinitions cannot change null eigenfunctions of your two-point function. So you can see this guy in the orange box, the two-point function as defined by the phi tildes. If you contract either x1 or x2 with an on-shell wave function and e to the ipx, with p on the mass shell, that needs to vanish if and only if the equivalent version without the tildes vanish. This is one consequence of only being able to make local healthy field redefinitions. And so this is why this last term also vanishes on shell. But the important point of this slide is that we have identified something which has a covariant or approximately covariant transformation. And this is important if we want to now identify physical quantities which are completely invariant under all field redefinitions. So that is it for part 2. All we've done is just taken the textbook construction of correlators and rearranged it into building blocks which have nice geometric relations and transformations. Now, the reason for doing this is to start to generalize everything that I've told you about already in part 1. So for instance, we can now start to try and identify things which are completely invariant under all field redefinitions, including derivatives. So we can find quantities built out of things in the Lagrangian, which are completely invariant under field redefinitions, and therefore must be physical and observable in amplitudes. So this is what I mean by generalized curvature invariance. You recall from part 1 that there's also an optimal basis, namely normal coordinates, where each Wilson coefficient maps nicely onto distinct kinematic structure in amplitudes. And we want to be able to do the same when we're making field redefinitions with derivatives. That's one possible application of this. And of course, because field redefinitions with derivatives is part and parcel of choosing a nice basis in the UV in which to match your theory, we hope we can start to understand how to better match UV theories in this general formalism, and so on and so forth. But the main takeaways from this talk are the following. I hope you've seen how field redefinitions generally make the on-shell behavior of Lagrangians difficult to see by eye. And this is essentially because any one Wilson coefficient is unphysical. Any one operator is going to combine with other operators to make a particular component of an amplitude, a particular coefficient multiplying a given kinematic structure in an amplitude. Now, geometry is a very useful tool to isolate things which transform invariantly or covariantly under field redefinitions transformations. And this allows us to isolate measurable quantities. And not only does this open up new routes for practical calculations, so you've seen how we managed to very efficiently calculate the contact piece in a 2 to n amplitude in Heft, which is normally quite difficult. But it can also shine light on conceptual methods, such as sort of decoupling in the scalar sector of the standard model and when we should use Heft versus Meft. And so with that, I just want to refer you to the clickable links here in the bibliography if you want to refer to the slides online. And thank you very much for your attention.